Welcome back to another HVAC-Engineering-Techie training video. Remember, these training videos are educational in nature and intended to help you with your career. Today's lesson is on steam systems, basics, and components. So we're going to go over the different things that make a steam system what it is. Now, steam systems are not used as much as they used to, but there are still systems in very large buildings or industrial complexes that you may come across. So remember, this channel talks all things HVAC, engineering design, construction equipment systems, test and balance, controls, efficiency, and performance. Before we start, I'd like to ask you a big favor to become a subscribing member. Just have to push that black button down there. Give me a thumbs up if you like that. It's totally free. It costs you nothing. It's totally painless for you to do, but it actually helps me a lot. Google uses that data to evaluate my videos, which actually keeps me on the air. So I really appreciate it if you do that, and I hope you get something out of this video. So let's get started on basic steam systems. Thank you. So now we're going to talk about steam basics. First of all, we'll look at a system to see what a normal system does. So this is a normal two-pipe steam system, even though there are one pipes, but those are mainly residential of the past. So this is a normal system. This happens to be a gravity return. And we'll talk about those in session S-17, which is on steam systems. We just want to get to know the components. So there's a boiler, and the boiler actually boils the water. So water is fed into the steam boiler from a deaerator tank. Now, it may be just a condensate tank, may not be a full deaerator. And we explained all that in S-16, what that actually does. But it actually has a level control, and the water's controlled, so it either gets condensate return or it puts fresh water into it, treated fresh water into it. And when the boiler needs water, then it will pump. These pumps will turn on, and they will pump the water into the boiler, keeping the boiler control where it should be. The boiler creates the steam. The steam goes through the distribution piping out to the load, and to the coils or heat exchangers, whatever they are. The coils condensate the steam. So when that part of the system needs heat, it puts steam into the coil, which transfers heat. And as it transfers it condenses back into water, and then this system back into the condensate and flows back to the deaerator tank. Steam traps keep the condensate separate from the steam. These steam traps are a very important part of the system. Condensate drains back to the condensate receiver via gravity flow or by vacuum or pumped, either one. It could be any of the three. So some steam system basics. Steam system heats water until it reaches a change of state from water to saturated steam, and at sea level that's 212 degrees at 14.6 psi. Applying additional heat to saturated steam will increase the pressure and temperature of the steam. Now that saturated steam does that. If you know the pressure of saturated steam, you know its temperature, which is handy. Applying additional heat to saturated steam away from the boiler water will superheat the steam. So if you don't have that body of water there and you take the saturated steam and heat it up, it becomes unsaturated, and all that water that was saturated in it now goes to be steam. So it's all vapor. Applying additional heat to superheated steam will increase its temperature, specific volume, and total heat, but not its pressure. So from low temperature up to saturated, up to boiling, saturation temperature, that has that benefit where we can know exactly what pressure it is if we know its temperature, or if we know the pressure, we know what temperature it is. But once it gets past that and goes to saturated to superheated steam, that no longer applies. So standard commercial steam system pressure ranges are 5 psi, which is 227 degrees, 15 psi, which is 250 degrees, 65 psi, which is 312 degrees, and 85 psi, which is 327, and 125 psi, which is 352. Now, there's nothing sacred about those numbers. You can set the boiler to produce any pressure you want, but these are just the normal ones. 5 is low. They actually can go as low as 1, and you can go above 125, but only if your steam system is designed with the right pressure piping. So if you go up to 250, you got to have 300-pound fittings and pipe. The 125 mainly is is the limit mainly for commercial systems. Some systems will run 100 psi. You can run any psi you want, but these are the standard ones. Okay, water boils at 212 at sea level to produce steam. As the pressure or altitude goes up, the temperature for which water boil goes up for saturated steam. After converting water to saturated steam, you can add additional heat, which superheats the steam, increasing its temperature and the total heat of the steam. Now, not to be confused by this, but as you change altitude, the actual temperature of steam goes down. So in other words, at sea level, it takes 212, but at 10,000 feet, it only takes 151, I'm sorry. So it takes a lot less heat as you go up because of the pressure. The pressure is much lower up there. Total heat of 1150 BTU per pound is required to convert water to 212 degrees at sea level. Now, it matters a little bit at what steam. This is actually starting at 75 degrees. If you had water at freezing 32 degrees, it'd take a little bit more heat, but not much, because most of the heat is at its transition point between water and steam. That's a whole lot of heat. The heat to heat the water from 75 to 212 is not much. All right, so here's a typical steam table, and this part here is saturated steam. This is 350 degree superheat and 600 degree superheat. Just to let you know, 600 superheat is power plant territory. You shouldn't have any of this in commercial. Even a lot of systems don't even use superheated steam at all. But if you do, it'll be in the 300 to 350 degree range. So these are the pressure of the system, its temperature, and the BTU per pound, and then the cubic foot per pound. So at 212 degrees, steam takes 26.79 cubic foot for 1 pound of steam. But if you take it to 15 psi, in other words, you pressurize it, you're up to 250 degree temperature and you're 1164 per pound. So the BTU goes up. But look at the cubic feet, it's 13.74 per pound. So you can see the steam is getting a lot heavier. It's got more saturated vapor into it, it got more water into it than the one at 212. And as you go up, that happens. You go to 65 psi, you get 312, and you get 5.47. Go to 85, you're at 4.43. You go to 125, you're at 3.21. So you can see that steam keeps getting denser and denser and denser because you're packing more and more energy into it, which is the steam is becoming more dense, which becomes it has more energy in it. Now, if you want to superheat it, and you got 15 pound steam, which is 250. So if you superheat it to 350, you're going to get 1,213 BTU per pound. If you go to 85 psi, you're 1199 per pound. So it's slightly going down. The BTU is going down, but the temperature is going up with that. And the reason we don't have one here, of course, is you're already at 350, so it's not going to superheat. You got to go beyond superheat. And these are the ones for 600 degrees. So the reason we go to superheat is because it packs more BTU per pound, so we can get a little more work out of the steam. So HVAC and plumbing steam systems are used for space heating, humidification, water heating, cooking. A lot of cooking uses live steam to cook. Steam-driven equipment such as pumps, chillers, generators, process and manufacturing. So those are normal uses for steam. Okay, British thermal unit, the BTU, the amount of energy required to raise 1 pound of water 1 degree Fahrenheit. So 1,000 BTU equals 1 pound of steam. Now these are just general terms that we use, and you can actually work a lot of these out yourself, but it's easier just to record them. So 34.5 pounds an hour equals 1 boiler horsepower, because we rate boilers by horsepower. 1 boiler horsepower equals 140 square foot of steam radiation. 34,500 BTU, 34,500 BTU equals 1 boiler horsepower. 1 gallon of number 2 oil equals 140,000 BTU. 1 cubic foot of gas equals 2,550 BTU an hour. 1 cubic foot of natural gas equals 1,000 BTU, plus or minus. Natural gas will be right around 1,000 BTU, but it may be a little more because sometimes there's other chemicals in the gas that make it burn a little hotter. kilowatt equals 3,413 BTU. 1 therm of natural gas equals 100,000 BTU. So these are normal factors that we use in designing steam systems that might be helpful to you. Now, steam systems are life safety systems, so they're heavily code driven. The steam systems design and construction have several codes that apply. The main one is the ASME pressure vessel and piping code, which is ASME B31.1. The ASME boiler pressure vessel code BPVC. The IMC chapter 12. NFP 31 oil fired, NFPA 54 gas fired, and NFPA 85 combustion hazards. FM or other insurance underwriters requirements, because anywhere you have a steam boiler, because they are life safety issues, they have to have special insurance. And so Factory Mutual or other uninsured riders will have certain requirements that you have to meet to be able to get the buildings insured. So that's important. EPA flue gas requirements. EPA has certain regulations on how much flue gas can be emitted. Boiler size and flows. So the small residential system might be 1.5 to 25 horsepower, or might be even less, but they're going to be small systems, which would be 52 pounds an hour to 863 pounds per hour. Commercial would be 15 to 80. Now, commercial could be higher. It could be 518 pounds to 2,760 pounds. A large commercial could be up to 800 horsepower. 600 horsepower seems to be a sweet spot for a lot of systems. That's 3,450 pounds an hour, or 27,600 pounds per hour. Now, there's one thing about size in boilers that we'll talk about in a second. The turn down ratio is very important because big steam boilers don't have really high turn downs. I mean, the turn down may be as high as 25%, and that's the case. You have a 600 horsepower boiler, then you got to be 150 horsepower is the minimum that boiler will do, which could be a problem. So we have to talk about that when we design. Now, industrial and electrical generation boilers may be much larger, but are not covered. I mean, they can be thousands of horsepower, but that's not a part of this course. Boiler efficiency. Normally, gas-fired boilers are 80% efficient. Just 20% never makes it out to the steam, but normally 80% does. Systems 40 to 70% depending upon system losses. So here's a depiction of a normally operating system where you see the gas input's 100%, and a combustion stack losses, that's the heat that goes up the flue, and cycling losses, which are losses when it's trying to change load, and those get up to 20%, and that's the difference between an 80% process from the boiler. But there are other systems in the steam plant. So there's poor insulation on the piping and steam trap losses. Sometimes traps leak or stick open, and so those take out another 10%. So instead of 80% to the load, we have 70%. And that's a pretty good steam operating plant, that if it gets 70% of the heat out to the load. Because one thing about poor insulation is, remember that the piping, everything, the whole piping system, the heat required to keep the pipe hot is a loss, because that heat turns that steam to condensate, and it never makes it to the rest of the load. So you have to have good piping insulation to make sure you're not turning a lot of your steam to condensate before it reaches a load. Now, normally a worse run plant would be one that has 25 combustion stack losses, 10% cycling losses, 15% poor insulation, and 10% trap losses, which it would be only 40% going out to the load. These are expensive losses, and these are all about maintenance. If you're not performing maintenance and operations, so this is really important in steam systems, especially big ones, to keep them operating efficiently. These are the ones that you should not have. Here's a boring subject, but the Tempe steam piping specifications. Low pressure steam, 0 to 25 psi, is normally 1/2 inch to 2 inch carbon steel. ASTM A53 grade B seamless, schedule 40 threaded. Threaded fittings are ASTM A234 125 pound. Low pressure steam, 2 inch and up, 2.5 inch and up for carbon steel, actually the same as the other one, exactly the same. Medium pressure steam, which is 24 to 125 psi, So we've separated ours into those two categories. 1/2 inch to 2 inch carbon steel A53 grade B seamless, 80 schedule 80 threaded. Threaded fittings are ASTM A234 300 pounds. So you see, to get up this 125 psi, the fittings now have gone from 125 psi to 300, and the piping has gone from schedule 40 to schedule 80. Medium pressure steam, again, for 2.5 inch and up, are the same. Schedule 80 welded fittings are STM 300 pounds. Condensate piping is 1/2 inch to 2 inch carbon steel ASTM A53 screwed, grade B seamless schedule 80 threaded, or ASTM A53 hot dip galvanized pipe. Cast iron threaded fittings are ASTM A234, 125 pounds or 150 pounds. Condensate drain may be type K copper with welded joints. So remember, the thing about a condensate drain is it's corrosive. That's pure water, and it's corrosive. So if you're going to put carbon steel, it has to be a heavier gauge, because they're accounting for part of it to be eaten away over time, so they put a thicker gauge. Or it's galvanized. You can run stainless steel too if you want, but most people don't because of cost. Or it can be copper, and copper is a really good system because it doesn't. The steam does not erode the copper. And 2.5 inch up can be carbon steel A53 screwed grade B seamless, schedule 80 welded, or ASTM A53 hot dipped galvanized pipe, or welded fittings with 125 to 150 pound condensate drains may be type copper with welded joints. We don't normally do copper 2.5 inch above because of cost, but you can do that. Clean steam should be 304L or 316 or 316L. Stainless steel pipe with welded fittings, schedule 40. Lower pressure at schedule 80 for medium pressure on clean steam. Remember, there's no condensate on clean steam. All right, so here's a boiler, and let's talk about regulations. So the regulations require that anything that's a pressure vessel, which the steam boiler is a pressure vessel, must be ASME rated and certified as a pressure vessel, which means it's had inspections, its welds have been x-rayed, and it's guaranteed to be a pressure vessel for the pressure rated. Not only is the boiler, but this is the first stop valve. So if you have a pipe coming out of a boiler with steam, and this valve may be right on top of the boiler, it may be over here in the pipe, but the pipe between the boiler and this first stop valve are considered part of the pressure vessel. So when the field guy welds this pipe up, it has to be field certified. He has to be a certified welder, and it has to be x-rayed, and it has to be the same condition as the vessel itself. So when you're building these, you keep the stop valve as close to the boiler as possible, so you don't have a lot of that, but you do have it. As a matter of fact, if you put the stop valve on the flange to the boiler, you're in good shape, because then you don't have any of that field weld. Now the pipe downstream must be by a certified welder, but does not require to be x-rayed and to be a full pressure vessel. All welds or pressure vessel or steam pipe within the pressure vessel boundary require certified. This is what I said. Boiler system design must consider maximum and minimum loads. Now here's what we're talking about, the turn down ratio. If a boiler has a 4:1 turn down ratio, then its minimum capacity is 25% of the boiler. A 100 horsepower boiler with a 4:1 turn down ratio will only run above 25 horsepower. If the boiler has a 10:1 ratio, it will run down to 10 horsepower. So this is really important, because if you have a steam load if you have a 100 horsepower boiler that has a turn down to 10 horsepower, and you require 1 horsepower for some load in there, it's not going to happen. So that's something you got to check out every once in a while. Single or multiple boilers may be required depending upon the load profile. The boiler turn down ratios, multiple boilers may be warranted. Multiple boilers provide a percent of redundancy, backup, or redundancy. Unequal size boilers, if the minimal load is small, unequal boilers size may be required. And here's an example. Here's a central plant where we have, in the winter we have 450 boiler horsepower required. In the spring we have 60 horsepower. During the summer we have 25. During the fall we have 150. And we have 3 250 horsepower boilers. So you would turn on, for winter, you would turn on 2 of them, and you would get 500 horsepower, so that's enough to do the load, and you'd have one in standby, which would be a good deal. During the spring with 60 horsepower, you would bring one on at 60 horsepower, so you'd have to turn on a 250 for that. 60, 250, if it has a turn down ratio of that, you're in good shape. If not, you got a problem. Summer is 25 horsepower, which this would have to be a 10 to 1. If this is a 4 to 1, then this is not going to work. So you'd have to do something differently. Well, the different thing you would do is you would have two boilers at 250 and one at 50 horsepower. So then during the winter, you'd run two of the boilers, the two big boilers. During the spring, you would run one of the big boilers, and it would meet your turn-down ratio. And during the summer, you'd run the small boiler, which this would be within its turn-down ratio. So that's how you would do that, by unequal-sized boilers. And then for the fall, you'd run one of the 250s at a good turn-down ratio. This is kind of important when you're considering load, especially in my territory, where we do have steam boilers, but we don't have a lot of load, so the turn-down ratio becomes really important. The pipes are hot, so this is steam safety. They're 250 to 350 degrees and could cause serious burns if touched. That sounds like that wouldn't be a problem, but I had a job one time. It was a solar-fired chiller, so we had a whole bunch of tracking collectors. We made 450-degree thermal oil, and the 450 oil ran a steam turbine, and it ran a generator and a chiller and a bunch of other stuff. So it was 450-degree oil. Well, the problem is this thermal oil, it went from like 4 centistokes when it was cold up to a half a centistoke where it was really hot. So we couldn't insulate the valves. The valves had to be put sideways because the packing, when it was really hot, the packing would drip oil. So we had to put catch pads underneath them. And I had to hang signs on these things saying, hot, do not touch. And when I'd bring guests there to show them the system, because it's a pretty exotic system, solar-powered system, and the first action, no matter who they are, a certified engineer, no matter what, they'd say, oh, really? And they'd put their finger and touch it. And that's immediately burnt the end of the finger. I mean, it would just char the end of the finger. And I'd just say, no, don't do that. Trust me, it's hot. Because they just don't think about it. They think hot water systems, yeah, you could touch it. It's got 180-degree water. You touch it till it's hot. But 450-degree, no. Don't do that. So remember, these systems are hot. High water level conditions. I still have scars on my arms from touching steam traps every once in a while when doing work on a steam system. So, and the scars they stay white. They never suntan after that. High water level conditions, when a boiler operates with an excessive amount of water, carryover and priming are likely to occur. As water rises above the horizontal center line of the boiler drum, the water surface or steam release surface area decreases. When water surface area is not sufficient enough for the steam to be released at a controlled velocity, carryover water droplets through the steam header occurs, can cause water hammer in the piping system. So remember, your piping system on a steam system don't like two things. They don't like air, and they don't like water. Now, they got condensate in there, but they're trying to push that in, but they don't want a pipe full of water. You know, if you have a pipe designed incorrectly for the steam load and has too much condensate in it, as the steam pushes it down the pipe, it can become a solid block of water. And when it becomes a solid block of water, it can cause water hammer. The reason is, remember, steam is moving at 20,000 feet per second or so. It's moving really, really fast, and water's moving really, really slow. So what happens here when you have too much water in a boiler, it basically fills the pipe up with water, and it can cause water hammer, which can burst the pipe, and then can cause live steam into the space. So this is important, but this one's more important. Low water level conditions. When a boiler operates with an inefficient amount of water, severe damage and in extremely rare cases, explosions can occur. With low water, tubes are uncovered and no longer cooled by the boiler water. The temperature of the metal increases rapidly, the metal strength is reduced, and collapse or rupture can occur, especially with superheated boilers. So we need to be aware of that. It's important. This is steam system safety is very important because live steam can be very dangerous when released, especially at high pressure. Like a power plant, if it's running 600 psi, 600 degree steam, it can be very dangerous. If a leak occurs, it can kill you. Because it'll just cut you in half. So that's important. And even the lower pressures that we run still can be dangerous. In the 19th century and early 20th century, many people lost their lives in steam boiler explosions caused by low water levels in the boiler, mainly with trains. Steam trains, if the operator, the fire control guy, if he lets the water level in the boiler get too low, then the superheated steam barrels become very, very hot and can explode. And all the pipes you see sticking out of this are basically the superheat pipes. So a lot of people lost their lives in trains. We learned a lot of steam by running trains, but boiler accidents also happened. This is an industrial boiler that blew up. This is a commercial boiler that blew up and knocked the side of the building out. A whole bunch of things can happen if you let that. So remember, make sure the water control is correct. It's really, really important. Steam equipment, what do we use? What kind of equipment do we use in steam? We have steam boilers, condensate receivers, deaerators, steam chillers, steam pumps, steam coils, steam heat exchangers, steam water heaters, steam humidifiers, steam-driven generators, water softeners, dealkalizers, steam economizers, and autoclaves. And we'll talk about all those. So there's probably more steam equipment, but not many. These are almost all that we use. One thing I didn't put in here is we do have some steam cookers directly. I didn't put any kitchen equipment in here, but that's another thing we use. Steam boilers. Okay, steam boilers come in 3 basic types and all kinds of sizes and configurations. But steam boilers are gas or oil-fired water tube, small to large capacity. So this is a water tube boiler. And we use mainly water tube boilers for smaller boilers, but exactly the opposite is true of industrial boilers. They may be water tube, but very, very large. So the reason is cost, because you could build a water tube boiler fairly easy, but the others are more expensive. But when you're trying to build a 1,000 horsepower or 2,000 horsepower boiler, it's done as a water tube boiler. So here's a water tube boiler, how it works. This boiler has a chamber down below where it pumps water in here. It's got water in this, and it has these tubes that go between this, and they go around the fire tube, and then they go up to a steam box. So this is the surface that causes the steam. So the water level in this boiler is probably right up here, something like that. And as it gets hot, the water level will be up here, and it basically as the water gets hotter and hotter, then it starts to put steam into the steam box, and the steam goes out the boiler. Water level control, makeup water, keeps this water where it needs to be. And this should be coming from a deaerator or from a condensate system. And these are the water tubes. Now, the fire, of course, fires down between the tubes and comes up around the tube in the boxes and goes out the flue. So this is the water tube boilers, and as the pressure's up, as the tubes get hotter and hotter, they drive it into steam, and the steam goes out the steam pipe. The hot gas, then is pumped in through the burner. It heats up the pipes, and the flue goes out, and the gas flue goes out, it goes around, goes out the flue. The water level keeps the water level control where it needs to be, and the makeup water keeps it so it's not a problem. And this is a water tube boiler. Superheat boiler is the same, can be a water tube boiler. And you see, instead of going right out the steam is generated just like the other water tube boiler right here at the water level, fills the steam box, and then the steam goes down and goes through a tube that's in the fire directly and out, and this becomes a superheated boiler. The water level is the same, feed is the same, except it's a superheated boiler. Gas or oil-fired fire tube boilers. Fire tube boilers are exactly the opposite. The fire's in the tubes, not the water. So what happens is you have the boiler full of water, and we have these tubes that the fire goes down in a fire tube and comes out, and then goes through all these smaller tubes which are in the water vessel, and then it goes out the flue. And up here, as this gets hotter and hotter and hotter, the steam is generated here at the steam box and goes out the steam supply pipe. the water level controller maintains the water feed level to this boiler. These gas-fired or oil-fired burners basically have a blower on them, and they induce the fuel, and it's ignited, and it heats this, and that's the way they work. Medium to large capacity for oil for fire tube boilers. And then we have cast iron sectionals. Now, cast iron sectionals are the oldest type of boiler, medium or large capacity, but the problem is they're heavy because they're made out of cast irons. So here's a cast iron boiler. You see these sections. Each section is actually normally, for little bitty ones, they're packaging it. But on bigger ones, they actually bring these to the site and construction on site because of the weight. So they'll put one section and bolt it together until they get all the sections together, and they pipe up to the steam box. So what happens, the water level keeps this boiler of cast iron sections full of water, and the heat goes through the center of those cast iron sectionals, heating up the cast iron. The flue comes out, flue gas goes around and comes out the flue. As this gets hot, it steam box and the steam goes out that direction. The water level control keeps the water makeup. Now, the one thing about water makeup I didn't mention, remember, it always has to be of greater pressure than the boiler, or else it'll never get in there. So if you have a 125-pound boiler doing 125 pound of steam, then this has to be higher than 125 pound, which means the pumps on the deaerator need to be high pressure pumps. So they have to be careful with that. Now, the reason cast iron sectionals were used is cast iron sectional is heavy and absorbs a lot of heat and transfers heat pretty well. So it can store a bunch of heat in the cast iron, makes it hot. The only thing about cast iron, they're low pressure. Should be 15 psi, should be maximum pressure you ever put it under, cast iron sectional. The tube boilers, whether it be water tube or air tube, can be more pressure. Water tube boilers can be the highest pressure. And then we have electric boilers. Of course, electric boilers are stage electric heat elements, and basically they have a water vessel, and we have electric elements on the inside that heat, and we have a water level control that keeps the water level the same, and of course the steam surface generates the steam and it goes out this. All steam vessels have a pressure relief valve. In case it gets too high a pressure, it pops open, and of course you have temperature probes. Now, I guess electric steam boilers is going to be used a lot more if all the climate extremists get their way and let us burn any more gas, which I think is going to be really hard to do. But if you have electric boilers, they just cost a whole lot to run. So condensate tanks, feed tanks. This is a condensate tank, not a deaerator, and we'll explain why. So basically we got condensate coming back into the system and drop it down here. We have makeup water that comes to the system, and then they're vented. They're naturally vented so they don't build up pressure, steam pressure, so they come down. Have a level controller on it, have a control panel to run these pumps. And when the boiler calls for water, one of these pumps turns on and sucks water out and delivers to the boiler. So this is the main feed water to the system. We have condensate tanks, and these are condensate tanks that are out in the system on pumped condensate return. So as the condensate flows back into here, it gets the water level goes up, and when it gets up high enough, then this controller clicks on a pump and delivers that water to a feed tank or to a deaerator. So these are tanks that are designed to pick up gravity, system feeds back to them, and pump it back to the boiler. Single pump or duplex pump, can have either one. Then we have a vacuum condensate tank pumps, and these actually provide a vacuum on the condensate line to be able to vacuum the condensate back into the system. And these are duplex. This is a skid, so it has duplex pumps and duplex pump controllers on the unit, and this is how they work, which is really strange. So what they have here is they have a regular condensate tank down here that gets the condensate, comes back in from the system. There is a trap right here, and I'll explain why. And this condensate, then as it builds up, is pumped back to the deaerator just like the others, except on top of it, on top of this thing right here, it has a hurler or a vacuum pump on it. Now, the vacuum pump's not like a regular vacuum pump. It's called a hurler pump. And what it does is this vacuum chamber has a float valve, and it has makeup water to keep water at a certain level. Okay, and then this pump sucks that water out and at high velocity sends it through a nozzle, an open nozzle. And that nozzle, that water hurling through that nozzle creates a vacuum on this vessel. So now this vacuum has a vacuum, and it goes down and it's connected to this vacuum pump or to the condensate receiver. So now this is under negative pressure, and it flows out to the condensate drain and keeps this whole condensate drain under negative pressure is what happens. And this right here is a input strainer, and it keeps the system to make sure it flows into this. So these Hurler pumps are important, and they have a lot of other controls on them, but they actually allow the vent line. It vents this system, even though it's because this here doesn't have to be negative pressure. It's just this little section right here where this pump generates that, and this is actually a steam injector. Now I've used steam injection on that one job I told you about where we had a solar deal. I use steam injection to get down to almost as low as pressure as you can. So you can get really low pressure one of these. So this is how they work. It's really strange to see them, but that's how they work. They're not regular vacuum pumps, because vacuum pump couldn't create as much vacuum as they need and be able to take some water with it. So that's what makes it different. Deaerators. Now this is a deaerator, main system receiver tank. It has one more pump than another receiver tank, and that's because what it's designed to do is to remove air and oxygen from the water. It does that by scrubbing it with steam. So here's how they work. So we get condensate back from the system, and the condensate, that's steam pipe. Right here's the condensate. It comes back. Condensate comes back and drops into this side of the tank right here. And this is the makeup water in case this water level gets too low. It puts the makeup water in here. And then this pumps, the deaerator pumps, it sucks the water out of here, and it pumps it up here and sprays it on the top of the deaerator tank. And this is live steam that's blowing in here through this water spray and thus deaerates it. Then it falls into the deaerator tank, where this water here has a lot less oxygen than this water. And then these pumps come on and pump it back to the boiler. And that's a deaerator. It's actually designed to make the boiler more efficient, because this water, number one, it's actually heating the water up with the live steam, and it's got less oxygen, so there'll be a lot less issues in the boiler like foaming and stuff like that. So these are deaerators that are sized for the correct size for the boiler. Steam scrubs the circuit, removes air and oxygen from the condensate. Pumps supply water to the boiler. Okay, steam-driven chillers. These are fun equipment. So centrifugal chiller, basically it has a turbine, steam turbine, that drives the centrifugal turbine. These are on big chillers, and people that have a lot of steam. So it's more economical for them to just run directly the chiller than it is to turn it into electricity and let the electricity do it. We have absorption chillers that use steam directly to heat the desiccant to drive the moisture out of it. And of course, these take a large cooling tower, because a cooling tower has to not only remove the load of the chiller, but it has to remove the heat of the steam. So these actually work pretty well. Absorbers are not very popular nowadays because they are complicated. We have steam pumps. These are, again, has a turbine, a steam turbine on the pump, and drives a centrifugal pump. A steam turbine is a little more complicated than an electric motor, so these require some different kind of talent in your staff. It can be base mounted, it can be turbine driven. Also, split case pumps can be large pumps, because it's pretty easy to get a big turbine. Coils, we have different kind of steam coils for steam. We have same side coils, which basically bring the steam in to the system. And how it actually works is, you see, this is a steam header, and it actually is connected directly to a steam tube inside of a tube. So we have an outer tube in gray, and we have a copper tube in the middle that goes down to the end and then stops. So the live steam goes down the middle of the copper tube and then exits and comes back through the gray tube back into the suction header. And this allows the condensate to flow right back down this way. So these are steam pipes, what I call same side. and of course the air flows through the coil to change the heat transfer from the air to the condensate. And these have, of course, aluminum fins normally on them, could be copper fins, to actually increase the area for heat transfer. 1 to 6 row, 8 to 18 fins per inch. You can get closer fin, but don't. That's a good option. And opposite side ones are a little easier to understand because the steam comes in and it flows down the main tube, which is connected to the fins in the coil, and then it gets the other side, its condensate comes out the condensate drain. And of course there's steam traps over here. So these are opposing side coils. 1 to 6 row again, 6 to 18 fins. Now remember, steam is really hot, so you don't need a lot of rows. Most hot water coils and hot water systems are 2 to 4 rows. There's a lot of steam coils that are 1 row, but you can get them up to 6 row if you want to transfer a lot of heat. Marine headers. The marine header is basically, go back to there. Marine header basically is a cleanable header. So instead of a pipe here, it's a chamber that you can remove the cover and you can clean these. In marine applications, when you got seawater, you get a lot of things coming in with seawater. So they basically are cleanable. Steam heat exchangers, shell and tube. Shell and tube, basically the steam comes in the barrel. The processed water comes in here, circulates here, or steam. These could be steam to steam, or they could be water. Normally the water, it comes in, goes this way, and then the condensate drops out the bottom. Small or large capacity can be high pressure because they're all designed with tubes. Plate and frame, it can be steam, where steam goes in one and condensate comes out the other, and then the processed water goes in here. But they're low pressure. They can't take real high pressure. They can take 10 to 15 psi, but that's about it. Low pressure drop, small footprint, really efficient heat exchanger. Welded plate, which is another flat plate, but it's all welded up same way. Steam water heaters. Now, water heaters are just like a vessel, and it has a steam bundle in here, a steam heat exchanger with the bundle directly in the water. So the steam flows through this heat exchanger and heats the interior water. So this has systems on it to keep it full of water. Steam humidifiers, direct steam insertion. This is a direct steam header, it goes in a duct, but it really should be clean steam, because if you're using raw steam, you can be putting the chemicals that you use in the steam to keep it from corroding. That's not good. It should be clean steam. Duct mounted, space mounted, can be space mounted if you want with a fan on it. And then we have indirect steam heaters, and these basically allow you to put a humidifier on our standard steam system without clean steam, because this is just a little like a humidifier. Actually, it's kind of what it is, and it allows this clean water in here. So this is coming from an RO system into this little tank, and we have the live steam from the system doing a heat exchanger in this tank, and it creates steam. So this is now pure steam. So this is dirty steam, and this is pure steam, and this will allow you to go to a steam humidifier into a space with clean steam. Duct or unit mounted, space mounted, can make humidification. Steam electric generators. This is shown as a small generator, can be a very big one, of course. And you put a turbine on here. Now this is a little 2-stage turbine. The one I used for that big job I did, was a 11-stage turbine. So it was a big long thing. It looked like a big power plant. Little generator, but big power plant, because I had to have a really efficient system. A generator, high pressure steam works best. Small to large generators. Now, water treatment. All steam systems need water treatment. Mainly we got water softeners or dealkalizers that take the calcium and magnesium out of the water before it delivers it to the boiler, because it's just going to cause you problems in the boiler. Now, the steam doesn't have it in it, right? The steam's clean because it drops all the contaminants back into the boiler. Just means if you don't do this, you're going to have a lot more stuff in the boiler than you want, or hard scale in the boiler instead of soft scale. Soft water supply to receiver or deaerator. Boiler water treatment. So we have anti-foaming agents that need to go in there. We have anti-scaling inhibitors. Remember that a boiler, if it foams a lot, that foam ends up getting pushed into the steam line, which then can lead to water carryover. So we don't want to foam. Anti-scaling inhibitors, we need to make sure some system's not scaling. And we have corrosion inhibitors. So we have two types of corrosion inhibitors. We have one that can go into the vessel, and another we normally inject directly into the steam header pipe, which is a means to it actually coats the piping. And pipe system inhibitors. And this is where they're at. These three here would be here. The anti-foaming agent, anti-scaling, and corrosion inhibitors would be pumped into the deaerator to be pumped into the boiler. And then we have a separate one just for the piping system that pumps right into there into the distributor of the pipe. So these don't pump unless the system is actively engaging steam. So that's the system. So normally it comes as a skid, lots of chemical, lots of water treatment in it. Now the water treatment is actually important. We use them in the cooling side for cooling towers and whatever, but these are kind of important for the boiler to work correctly. Now we have steam economizers. These are actually intended to help improve the efficiency of the steam systems. This is a flue stack economizer, which it actually goes on the flue stack of a boiler, and as the feed water is put in, it heats the feed water up, and that improves the efficiency of the system because you don't have to heat the feed water near as high. We're preheating the feed water. This is always important. The two things in efficiency in a steam system is one, maximum condensate return. Every drop or every pound of condensate you don't return, you have to make anew, which takes more energy because condensate's normally hot. It's right around 200, 212 degrees, right below steam generation. So it's normally hot. So that you want. Want to get as much of that as you want, and you want as hot as feed water as you can get. And that includes economizers to pump up the temperature of the feed water. Captures flue heat for feed water. And we have flash steam economizers. So anytime in a system, let's say you have a 125-pound steam system, it goes to a coil, it goes to its trap. The trap lets out the steam, which is going to be 350 degrees, right? 125-pound steam is going to be 353 or whatever it is. So that water is going to be 300 degrees. Now it's under pressure, so it's not steam. It comes out because it's under 125 psi pressure. It goes down. And now if you're going to dump that, if you dump it into a deaerator, it's okay. It can use that steam heat. But if you're dumping it anywhere else, it's going to flash immediately to steam. If you dump it to a condensate, a floor sink to get rid of it, because you don't have a condensate receiver close, it will flash immediately to steam and provide all kinds of steam into the space, because now it's going from 125 psi at 353 degrees to 75 degrees at zero pressure, so it's definitely going to flash. So what these do is actually let it flash in this vessel, and then this vessel has a heat exchanger. It takes that heat out of it for the feed water, and it has some fresh water it squirts in there and allows it to go to the drain. So this is a feed water recovery, captures flash steam heat for feed water and allows the system to get more efficient. Now steam autoclaves are used in hospitals to actually clean the utensils, the operating utensils and operating materials. So they heat it up to a temperature enough to be able to kill all pathogens and all viruses. You know, they're already washed, but now they're going to steam clean them, and that actually is why they use steam autoclaves. They must have clean steam. You can't use dirty steam inside an autoclave. May need a pressure reducing station to provide correct steam pressure. Normally the steam pressure, these is low, 5 pounds or so. Direct steam uses a steam-to-steam heat exchanger to turn pure water into steam, like I showed you before. Pressure reducing stations are used to, system components we're going to talk about is pressure reducing stations, flash tanks, boiler blowdown systems, steam valves, steam control valves, steam traps, strainers, expansion joints, piping specialties. So pressure reducing stations. This is where, say you have an 85-pound steam system, but you have something that has to be 5 pounds. So then you put a pressure reducing station in, so the live steam comes up, goes through the pressure reducing valve, which reduces it to whatever is required, and then it goes out. We have a couple other things here. We have a steam trap and a dirt leg. We have a bypass in case you need emergency bypass. But the problem with the bypass is it's very difficult with a manual bypass to create the correct drop. So this needs to be temporary only. And this is a pressure relief valve in case this pressure gets higher than what you need. It will dump it. So that would be the only saving grace of trying to use this. If you got too high a pressure, it's going to dump it. offline during maintenance. If you have a single one and you got to work on this valve, then when you work on this valve, this system's offline. If you have a dual system, then you can work on one and run the other one. Or sometimes you have duals if you have a huge fluctuating load down here and it's too much fluctuation for one valve. You might run two in tandem so that the two valves can go much lower than this could go. Always online due to dual units. Condensate flash tanks. This is a condensate flash tank, lowers temperature steam prior to dumping the drain. This one's not a recovery tank. This is just to get the steam to quit from venting. So it pumps cold water into it and lets it go to the drain. Provides raw steam to vent to atmosphere. Boiler blowdown systems. Okay, now boilers have maintenance issues, and one is to get rid of the crud that's on top of the water. If it foams at all or any debris floats, it'll float right to the top of the water, and then other debris will be heavy and they'll go clear down to the bottom of the boiler. So you need to keep those clean. So we have a top boiler from foam and solids from the boiler, and it sucks water right off the top to get rid of that. It can be a manual blowdown. This is a surface blowdown, so this allows, it should be right up there at the surface, but you open that valve and it'll suck the stuff off that to drain. And if you want to blow down the bottom, you open that valve and it'll suck the stuff off the bottom and put it to drain. And this needs to be a standard maintenance routine, how often you do it. Now, the surface one is done much more often than the down one, the blow down on the bottom, because we don't get that many solids floating to the bottom. You do have to do it, but you don't have to do it near as often as you should do the top. You can get a continuous blow down where you have this blow down. It's a balance valve, so you're going to take a certain amount of water always off the top, run it through a heat exchanger, and then run it down to a flash tank and let it go to drain. You can do that. You can balance this, and this one's manual. Just do it every once in a while. Or you can have an automatic blow down. And what it does is it has a TDS. It has a valve here, and then it has a sensor, a TDS sensor in the boiler, and tells when it gets in this drain line, and it turns it on. It can also be timed to turn it on automatically and let it blow down to a heat exchanger, and just like the other one. And then the bottom's a manual blow down. So you can have any of those three types of blowdowns on a boiler. I've installed these before on boilers where we let this does it once a day or twice a day, and this one still remain manual. Bottom blowdown removes collection solid from the bottom of the boiler, normally manual blowdown. Steam valves, shutoff valves. So we have shutoff valves, gate valves, ball valves. Gate valves are normally using really large valves. And then we have ball valves for the smaller balls. And these all need to be rated for steam, temperature, and pressure. Globe valves are used for controlling steam if you need to. Butterfly valves for very large and can be used on steam as long as they're rated for steam. Check valves are always swing check valves. And they again need to be steam rated and always pressure rated, so you may need to have 300-pound valves and pressures if you have a high pressure system. And then we have swing check and spring checks, and these spring checks basically the steam overcomes the spring. Then we have pressure reducing valves, which are a diaphragm, and they're downstream regulated, so you take a downstream pressure tube and pipe it up, and it regulates. Downstream pressure regulates half the pressure wafer in here to control the steam. We have pressure relief valves, which are designed to pop off at certain pressures. Steam control valves. Now, steam control valves are normally globe, 1/2 inch to 6 inch. And the thing is a difference, this doesn't show very well, but steam valves should always have a temperature extension to keep the actuator away from the heat of the steam valve. So normally these have a 2 or 3 inch lift on them to keep away. This is a globe valve. Of course, the globe is parabolic, so it's somewhat linear. Can have ball valves. Again, we need an extension to get them out of the heat range. Ball valves can be a 1/2 inch to 3 inch. Butterfly control valves can be large. If you're going to use them for control, they need to have a fishtail valve that be able to do a 60-degree control. Steam traps. Now, steam traps come in different flavors, and there's all kinds of different ones. So my favorite was always an Armstrong trap, but Sarco makes a good one also. This is a bucket trap. Now, what happens in a bucket trap? We have the inlet. Steam comes in here and comes to the bottom of this unit, and if it's got a lot of air in it, it will blip this trap. It's a bucket. It's an inverted bucket, so it's hollow up here, and the air will build up in this bucket as steam and bucket, and it'll lift it. And when it lifts it, it opens this little valve here, which lets it exit to the condensate drain. So we want to get rid of all the air, and steam, live steam, pushes it open, brings it back, pushes it open, brings it back, and there's a little hole here to allow it to seep out. And when this gets full of water, it also the steam, if it's live steam, it has a certain buoyancy, but when it's water, it has a different buoyancy and lifts it up and allows the water out. So that's a bucket trap. The one thing about bucket traps, they can't pump that force of going up and down actually can help pump the condensate up. So it puts a little more pressure on the condensate than it would be otherwise. May also have a thermostatic trap. It can have a thermostatic trap either here or here to allow it to go to the other. A float trap, which is Sarco makes a lot of these, so they have a big float in here, and a float opens up the drain to take it to get out of there. So this is the inlet, this is the outlet. They can also be, this will do a higher volume than a bucket trap. May also have a thermostatic port right up here to let air out. And then we have thermostatic steam traps, which remove air from the system, and these are all temperature based. They have a temperature bellows in there, so as soon as the live steam comes up and heats it, it closes the valve. So on a lot of large systems, when we start them up, we actually may open a manual valve somewhere and watch it, and as soon as steam starts coming out, shut it, because you need quite a few of these to get rid of the air in the system. That's really important. Vacuum breaker opens to release vacuum caused by cooling steam. So as the steam condenses, it actually goes down in pressure and it will create a vacuum inside the pipe. So we put vacuum breakers on them to allow the system to induce air when you're shutting it down. Strainers, you have standard strainers. Could be small pipe strainers where the water flowing in water goes through the strainer and out. It can be small, it can come up to maybe 2 inches or so. And then we have regular Y strainers, which can be large, where the water flows through the sieve and then out the system. Strainer sieves, this is something that's not readily available, which I don't know why, but it's not. So if you have a standard screen size for steam is 1/8 1/4 inch, and these are the different, this is steam, this is water, this is steam systems, this is the pipe size, this is the coarse sieve, and this is a fine sieve. So it might be an 80 sieve or whatever. These are the sieves you could get. Now that, believe it or not, this system is not really available, and I don't know why. This is a perforation size. So this is a micron size, and this is the mesh size. 1/12 inch, 1/14 inch, and it goes down to those different sizes. It gives you an idea how big they are. Standard screen size, 1/8 1/4. Startup screen size is 1/32 to 1/16. So you can have startup sieves in these also. Steam pipe expansion. Now remember, steam pipe is going to have a lot more expansion than a hot water pipe because it's a lot higher temperature. So there can be expansion loops like this where it allows this pipe to move this way and this way. It can have pipe expansion mechanical couplings where I have a bellows here. So there's no possibility of leaks around the system around this one. It allows movement in that direction. It's an extra coupling, which are pipe flex connections. Bellows flex connections are all stainless steel bellows. Steam piping specialties, gauge pigtail siphons. Now on steam, you don't want the fluctuations of pressure going to the gauge or to the sensor because it'll fluctuate a lot. So what we do is we call pigtails, and what happens here is the pipe comes up and goes around and goes out to the gauge. So what it does, it stays half full of water all the time, and it allows some variance between the steam pressure because this won't drain out. This pipe here, even when the steam's gone, this will still have water in it, and that protects the gauge from that. At all pressure gauges and sensors, Protects the pressure gauge from high temperature and steam pressure fluctuations. Dirt legs are important, so anytime you have a steam device that like this comes out of the coil, or steam turns direction, this is actually a dirt leg. And dirt legs collect solids from the steam, provides water reservoir for the trap, so there's a little more water here for the trap. Add equipment trap connections, long running steam mains, because if you get along, there's a design, when you design this, there's a rule of how far you go before you have to do a steam trap, because you may have to change the gradient, but you also know the water is flowing this way, so you want to take it out of the steam line to allow more room for the steam. And so you do that along running steam mains. That main changes the direction for large branch takeoff. So if you change, say you're going down a basement and you need to go up to the second floor, well, where that pipe turns up, there needs to be a dirt leg and a steam trap. Steam trap, because it will cause a lot of condensate right there. And at the end of main. So large branches at the end of main always needs a steam trap. Dirt leg dimensions. This is out of the design manual. So this is the pipe size, and this is the size your dirt leg needs to be, which is pipe size, and its length, how long it needs to be for that pipe size. So you can see the short ones don't need to be very long, but the bigger ones need to be longer. And that's Steam Specialties. So you got through all of that. Appreciate you being here. Thank you for taking the course. I appreciate you being a subscribing member. Have a great day, and I'll catch you on the next one. Thank you.